Okay, so time is coming. So can I see this slide? Okay. So yes, I'd like to start this second FCT webinar, which named the Frontiers of Concrete Technology. And time is coming. So can I see this slide? Okay. So I'm a title member from Nagoya University, Japan, and I'm one of the organizer of the this webinar. And today I am a moderator of this webinar. So today's title is Aging Management of Concrete Structures in Nuclear Power Plants, which is will be focused on the internal swelling reaction of concrete. Especially alkali-silicium reaction and the irradiation of the concrete. So this webinar is organized by the Japan Society of Civil Engineers. So firstly, I'd like to introduce about the JSCE. Okay, so yes, JSCE has a long history, more than 100 years, and it has several committees. One of them is a concrete committee, and this webinar is one of the activity of concrete committee. And the concrete committee published a standard specification for concrete structure as shown here, and it is in English, and we can all be, yes, we can download in the website freely. So yes, please visit it. And also, Concrete Committee issued a newsletter every 3 months, almost 3 months, about the latest activities of our Concrete Committee. And also, we are doing the international seminar, as shown here, with Asian country and sometimes European countries. But now it is very difficult to open this international seminar face-to-face due to the COVID-19. So this is the reason why this webinar was newly launched from April in this year. Okay, so today we could invite very famous researchers. First researcher is Dr. Miguel Ferreira from Finland. And the second researcher is Dr. Ippei Maruyama from Japan. And they will give us the advanced information of aging management of concrete structure in nuclear power plants. And after that, we will have a panel discussion coordinated by the invited moderator, who is Dr. Kenichiro Nakarai from Hiroshima University, Japan. Okay. So in fact, this webinar was from the special issue of Journal of Advanced Concrete Technology. So this journal, JSCE, is an open access international journal, and this research field covered by this journal is concrete materials, concrete structures, and maintenance, rehabilitation, and the other related subject of concrete engineering field. And also, this journal had some of the several remarkable points shown here. And one of them is a special issue. And this webinar is from second special issue. And also, Dr. Miguel Ferreira and Professor Ippei Maruyama is an editor of this second special issue. And also, Professor Ippei Maruyama is an editor-in-chief of JSCE. So, Professor, do you have any additional comment?
Thank you, Miura Sensei, and hello, everybody. So I'm editor-in-chief of this journal, Journal of Advanced Concrete, published from the JCI. And as the Professor Miura remarks, we select the outstanding papers, 3 outstanding papers per year, and the publication is relatively fast and no charges, and it became open access. So if you want to publish the paper for all the to all over the world, please try to submit the important manuscript to our journal. Thank you.
Okay, thanks so much, Professor Ippei Maruyama. So I'd like to go on the introduction. So this is today's schedule. Now we are in here, introduction. And after that, we will have an overview of management of concrete structure in nuclear power plants from two invited researchers, because we are not so familiar with this field. So firstly, we will learn about the what management of concrete structure in nuclear power plant is. So after this, we will have two presentations from Dr. Ferreira, Dr. Maruyama, for 30 minutes for each. And we will have a short Q&A from audience. I will select the question and comment. And after this presentation, we will have a panel discussion coordinated by Dr. Kencho Nakarai. Okay, for the Q&A, if you have some comment or question, please use Q&A box, which is a function of the Zoom, as shown here. So if you have a comment, question, please write it in the Q&A box with your name and your affiliation, please. And after this event, we will send the follow-up questionnaire to all of the attendees, and please reply to us your impression of this webinar. And also, we will have another way to join this webinar by using a YouTube live streaming. And you can see this URL, which was already distributed by email. So you can join this URL. So I'd like to finish the introduction of this webinar. And I'd like to move on the overview of management of concrete structure in nuclear power plants. Before that, I'd like to introduce two invited researchers. First invited researcher is Dr. Miguel Ferreira. He is a senior scientist at VTT Technical Research Center of Finland, Ltd. And also he was assistant professor at the University of Minho, Portugal. As you know, he has many research achievement and the contribution of concrete field. So I will introduce the selected his biography. I'm sorry about that. So Dr. Miguel Ferreira mainly studied on the provided innovative solution developed under R&D environment to address concrete issue, aiming at lowering the carbon footprint of concrete and contributing to a more sustainable construction practice. His research interests cover concrete deterioration mechanism and their synergetic effects, service life engineering, including design, in-situ assessment, life cycle analysis, and aging management system for concrete infrastructures. So recent his interests include nuclear power plant aging management of concrete structure and the non-destructive evaluation of reinforced concrete. And also he is now the coordinator of the European Commission funded research project, ACES. And also he is a coordinator of the Finnish research program of nuclear power plant safety, SAFIR 2022 research project CONAGE. So as shown here, so you can understand that he is now dealing with the very huge research project related to the nuclear power plant. And the second invited researcher is Dr. Ippei Maruyama. And also, as you know, he also have many research achievement and contributions. So I will introduce the selected his biography as well. I'm sorry about that again. So Dr. Ippei Maruyama is a professor of graduate school of environmental studies at Nagoya University. And also he is a professor of graduate school of engineering at the University of Tokyo with cross appointment. So he is a material scientist and a concrete engineer whose main research interests concern advancing understanding of the relationship between the microstructure, chemistry, and the properties of cementitious materials and performance of concrete structure. So he is currently a lead researcher with several national projects. First one is soundness evaluation of concrete structures exposed to neutron and gamma ray radiation. This is one of the topics of this webinar. Second, enhancement of soundness evaluation procedure of concrete structures in nuclear power plant using data of harvested materials from decommissioning plants. Third, evaluation of concrete contamination of radioactive material in Fukushima Daiichi plant. And fourth, impact of drying on cement-based materials from atomic scale to structure scale. So as you can see, these are a brief biography. So you can understand that there are very famous researchers all over the world, and there are now dealing with the very big, huge research project related to the nuclear power plant. So I think it is very good, wonderful opportunity to listen to their lecture today. Oh, sorry. So now I'd like to start overview of management of concrete structure in nuclear power plants. So yes, okay. Please start, Dr. Miguel or Professor Maruyama, if you prepared.
Hello, can you hear me?
Yes, I can hear you.
And I hope you can see the presentation as well. So I think before we start with the presentation, I would just like to thank Professor Maruyama and also Dr. Miura for the invitation to participate in this webinar. It's really an honor to be here today and to talk about topics of concrete and aging management in nuclear power plants, which are topics I really am dear to. And I would also like to congratulate the Japan Society of Civil Engineers for this webinar. I think it's an excellent format to be adopted, and also taking it forward in English, I think is an amazing step, as well as it increases the outreach and really allows for the dissemination of your objectives, and also dissemination of information and knowledge regarding civil engineering. So I think that's really a step in the right direction, and congratulate you on that. I don't know if Professor Maruyama would like to say something before we start.
Shortly. Thank you very much for giving me an opportunity to speak about the current the activity relating to the aging management of concrete structures. So especially for the Professor Miura and Professor Nagai and Professor Nakarai. Thank you very much. Okay, thank you. That's good.
Okay, so let's start. As Professor Miura said, this first presentation is an overview of the management of concrete structures in nuclear power plants, and both Professor Maruyama and myself will give this presentation, giving you a brief overview. Here we have the table of content, and you can see by the table of content that we're trying to provide you some understanding of the aspects related to aging management of concrete structures in the nuclear industry. There's a little bit of statistics about nuclear power plants, the aging of power plants in Europe and Japan. We cover a little bit about the standards and the different types of reactors. We go a little bit more specific into concrete aging issues related to nuclear power plants, and the functions for the reinforced concrete structures. And then we talk about the aging management approach in both in Japan and in Finland. And then we talk about a little bit about the R&D in support of the long-term operation of nuclear power plants. And then we end with some projects from Europe and from Japan. So currently there are approximately 443 nuclear power plants operating worldwide. This number might be off by 1 or 2 or 3 as it's constantly changing. So this represents, if we look at these numbers and we look at the figure there, we see that 2/3 of these, 67%, are already over the age of 30. And more than a quarter, 27%, are even over the age of 40. So we have a lot of power plants that are aging, and most of these power plants were received in the beginning an operating license for only 40 years. So these plants have reached this age, or reaching this age, or in some cases have already passed this age. And we know that when structures age, their performance starts to decline. This is natural. Subject to different types of loading, mechanical and from the environment. And that is the main reason why we have to have in place a program that manages the aging of reinforced concrete structures, whether we're talking about power plants or different kinds of infrastructure as well. And here are a few examples of nuclear power plants in Europe that have had some concrete aging deterioration issues. These issues have been reported, and I have taken this information from an IAEA document and the references given there. So obviously there are many more cases of aging that have not been reported, or at least have only been reported to the national regulator. So it's not very easy to get access to all this kind of information. And sometimes also it's the case that, very often it's the case that this information is confidential and is not reported, so it can't be even accessed. But if we look at some of the examples we see here, I've just highlighted a few, so I'm not going to go through all of those in detail, but we can see aspects like loss of pre-stressing forces, corrosion of the steel liner, carbonation in ASR, again, corrosion of the liner, shrinkage and creep, larger than expected. So all these expressions, loss of pre-stressing and corrosion, etc., are common for civil engineers, but in the context of nuclear structures, it can be a little bit different due to the uniqueness of the structures. And here is one case that I would like to highlight, and here we had ASR. It was found in the roof ring beam. So we have the containment structure, and then on top of the containment structure, there's a beam, a circular beam around the roof. And there was very poor drainage on top of that roof. So there was accumulation of water. And because of this accumulation of water, the humidity was high. And the aggregate was reactive. So ASR occurred on that ring beam. And in addition to that, on the upper part of the containment structure, and this you can see in the photograph, there's been extensive carbonation of the reinforcement due to poor concrete cover, and of course, corrosion and spoiling of the concrete cover. So all of the aging deterioration mechanisms that affect concrete structures that I can think of, there's one that's unique to nuclear power plants, and that is the deterioration that is induced by the neutron and gamma radiation. And this Professor Maruyama will talk a little bit about later. Otherwise, the concrete structures of the nuclear power plants are subject to the same aging mechanisms, chloride-induced corrosion, ASR, sulfate attack, etc. However, what makes the aging different in the case of nuclear power plants is the uniqueness of the structures themselves. The containment building, for example, is a 1 meter thick or more structure, and it's very heavily reinforced, more than conventional structures, with pre-stressing tendons, sometimes both in horizontal and vertical directions, and it can have a steel liner embedded or on the surface. So this makes, and sometimes there's even a double containment. So this makes the typologies that we are dealing with quite unique, and we don't have experience with those kind of typologies and aging mechanisms. So now about in Japan, Professor Maruyama.
Yeah, thank you. I will briefly mention about the status of Japan. This figure showing the current status of the nuclear power plants in Japan. So if you look at this figure, I'm really sorry that the words are in Japanese, but you can recognize the numbers. The number showing the age of the nuclear power plants, as you recognize that the many of the nuclear power plants in Japan also beyond this above the 30 years. So we really need to investigate or prove that the soundness of the structure of these kind of nuclear power plants. And after the Fukushima accident, situation about the nuclear power plants in Japan was a little bit changed or dramatically changed. And currently 10 units has restarted, and 6 units got the permission to make installation change, and 11 units are under examination. So 24 units are under decommissioning due to reasons brought by social environment change after the Fukushima Daiichi accident. So even though the many nuclear power plants are will be decommissioned, still the utilities want to operate the nuclear power plants. That is our situation. Could you go to the next one? Since in case of Japan, the new plant construction is difficult under the social environment. So long-term operation of nuclear power plants is a crucial problem for the utilities. And for the long-term operation, the cables, reactor pressure vessel, and the concrete structures in the nuclear power plants are difficult to replace, or physically it's possible, but economically it is very difficult. So the aging management for these things are very significant. In Japan, we concern seismic performance of the nuclear power plants also. So in this sense, the concrete strength and the stiffness change are crucial. And generally, the visual inspection, periodical visual inspection is conducted as a normal maintenance. And additionally, evaluation of the concrete performance by using the core samples is conducted. So, so that is the situation of the nuclear power plants in Japan. Please go ahead.
Thank you. So there are standards. There are standards, and these are many different levels of standards and different origins. And the IAEA, this stands for the International Agency of Atomic Energy, has safety standards that reflect international consensus on what is considered to be high level of safety for protecting the people and the environment. And these standards cover all types of nuclear and radiation applications. And they come in 3 different types. They can be safety standard fundamentals, they can be safety requirements, and can be safety guides. And in the figure here, we see in the middle and the top, the safety requirement, safety of nuclear power plants 2/2. So this is for the commissioning and operation of nuclear power plants. There is SSR 1/2, which is for the design. But since we're talking about aging and management, we are focusing more on the operation of the power plants as well. In this document, it describes the requirements that have to be met to ensure the safe operation of the power plant and the transition from operation to decommissioning of the power plant as well. And this includes things such as long-term operation of power plant, the aging of power plant, periodic safety reviews, probabilistic safety analysis, and risk-informed decision-making processes. So it gives very general guidance. And then if we go one level lower, we come to the safety guides, and these safety guides give a little bit more detailed information. And in the safety guide SSG 48, the title, I will read it for you, is Aging Management and Development of a Program for Long-Term Operation of Nuclear Power Plants. So this is relatively recent, from 2018. This gives more additional information and gives recommendations on how to achieve the requirements related to aging management and the long-term operation of power plants. And then there are other documents. There are many. Below the guidelines, we have technical reports, which are SREs, and there are many of these. And all these documents are publicly available. They can be downloaded from the IAEA website. And some of them come in different languages. I'm not sure if they are available in Japanese, but at least in English, and some of the languages they are available. One report series that is of interest, of course, is the Aging Management of Nuclear Power Plants, IGOL. IGOL stands for International Generic Aging Lessons Learned. And this is a document that contains aging management review tables and practices of aging management and time-limited aging analysis that member states have used and have approved and have been compiled together. So basically, this is a compilation of kind of operational experience, successful operational experience that will allow the owners to learn from that and adapt that for their specific cases. And there are other documents. There are, for example, not mentioned in the slide, but there are, for example, proactive management of aging for nuclear power plants as opposed to a reactive management and many others. So if you are interested, I would encourage you to look into these a little bit more. There's a lot of information, but not very much of this. This is general, more high-level information and not very specific to concrete structures. So it talks about SSC's system structures and components in a generic sense. I have taken one figure out of that, and this is quite a well-known figure. This is the Plan, Do, Check, Act cycle of aging management. You might have seen this in other contexts. So this allows, or this provides a framework for coordinating all the activities related to the aging management throughout the lifetime of the structure. It gives guidance on how to understand, how to prevent, how to detect, how to monitor, and how to mitigate the aging. So there's a lot of information on this as well in the IAEA documents, and I would encourage you to look into this in depth, as most aging management programs are developed based on this framework. Oh, sorry. Did I jump a slide? Have I jumped a slide? No. Okay. So in this slide, we want to provide you with a background on the evolution of reactor design. So many people ask, why have reactors been designed for 40 years when we can design bridges already for longer service lives than that? And the reason is that the limitation of 40 years wasn't a scientific or engineering limitation, but it was a limitation by the Atomic Energy Act that limited all operating licenses of reactors to 40 years. So it was never really a question of technical performance. And that is why many plants that are operational, that have been designed for 40 years, operational 40 years, they are actually now already performing, in some cases, up to 50, and they have intentions to go up to 60 as well. So this 40-year design life was never an engineering barrier. And there are different types of nuclear reactors, different types of designs, and they're usually called generations. And they can be generation 1, 2, 3 to 4, and there's even a generation 3+. So and you can see in the bottom of the slide a kind of timeline when generations of reactors came more or less into play. So generation 1 are prototype reactors, and these were developed in the 50s and the 60s, and most of these are shut down. And what we know today are mostly generation 2 reactors, and these are commercial reactors producing electrical energy. And these represent mainly operated reactors that are operated in France, in Japan, in the US, in Russia, and many European countries. So this refers to the large portion of the reactors that are operational today. They are basically designed for 40-year service life, but many of these are now looking for lifetime extension up to 50 and 60 years. And typical reactor types that are included in generation 2 are these PWRs, which are pressurized water reactors, the CANDU, which is a Canada deuterium uranium reactors. We have BWRs, which are boiling water reactors. We have AGRs, which are advanced gas-cooled reactors, and then we have VVERs, which are Russian design, and I can't read that word, I'm sorry. And then we have generation 3 reactors, which are advanced light water reactors, and generation 3+, which are near-term deployment. And these represent advanced reactors, so they are more, they have improved performance, improved design in their longer operational lifetimes. I think the first advanced reactor that was built was actually in Japan, if I'm not mistaken, the Kashiwazaki Kariwa power plant. I hope I've said that properly. So these generation 3 reactors are looking at a longer operational life, and they're typically designed already for a 60-year operation, but with the potential to go beyond that to 60 to 80. But this requires that R&D is supporting and supporting this life extension beyond 60 years. And then we have generation 4, which are novel designs that are under development, and they are expected to become commercial maybe in the late 30s, 40s, 2040s. Professor Maruyama.
Okay, thank you. Regarding the concrete aging issues in nuclear power plants, and as the Miguel said, that for the extension of the life of the nuclear power plants, we have to evaluate and prove the soundness of the concrete structures, and for that purpose, there's many discussions, and there is a reference and published from the United States US NRC. The reference number is New Reg CR 7153 Volume 4, and this is published in 2014. And based on a discussion among experts in the related field, this document identified the following issues to be studied. So the one is creep of post tension. The impact of moisture on the creep, multi-axial impact, the coupling with accidental loading, those things are, we have the qualitative information, but the quantitative information, it is very difficult to predict. For this purpose, we need additional research. And the impact of the irradiation on the concrete, also, we have some basic information, but still everything is not clarified yet. So we need additional research on the impact of the irradiation on concrete. ASR also quite harmful for the nuclear power plant, you can imagine. And still the large gap between the laboratory studies and the real structure phenomena. So we need the knowledge to bridge the gap between these things. In addition to this, the boric acid attack, the corrosion and the stress corrosion cracking of the tendons, and corrosion of the inaccessible side of the liner, these are also the harmful or difficult to assess. So therefore, these kind of topics are summarized and enhanced to promote, to do the research on these issues. Could you go next? So the concrete, but there is some difference, the concrete in nuclear power plants and the concrete used in general civil infrastructures. So that is related to the required functions. So the usage function, this is very general. The function is common to the general civil infrastructures. But the other than this is a little bit the specific or characteristic to the functions of concrete in a nuclear power plant. So supporting function is to support the equipment to generate the electricity. The pressure proof function is for the accident. And the shield function is to attenuate the radiation from the reactor. And a leak-proof function and a negative pressure holding function are the functions to keep the safe conditions against the radioactive materials. So the secondary accident prevention function, this is the this is a kind of a meta function, which means that the building elements shall not be damaged, fallen, or overturned so as to interfere with the functioning of more important facilities. So, we have to think about the any kind of the accidental phenomena and to keep the safe condition of the nuclear power plants. So the integrity or soundness of the concrete member should be considered with respect to these required functions. Thank you, Miguel. That's okay. And in case of the aging management of concrete structures in Japan, after the Fukushima accident, our new nuclear reactor regulation law came into force on July 8, 2013, and an approval system of extension of operation period of nuclear power plants is introduced. So the car companies are allowed to operate nuclear power plants up to 40 years. And after that, they can apply permission to extend operation period for just one time. So in general, the lifespan is 40 years. But if we got the permission, if we get the permission from the regulatory body, we can, the utility can extend the operation period up to 60 years. The extended operation period of a nuclear power plant will be at most 20 years, as I mentioned. So, so this is a schematic figure for the how to investigate or evaluate the soundness of a concrete structure. So after the start of the operation, every 10 years, utilities conduct the periodic safety review every 10 years. And after the 30 years of the construction, they will do the plant life management. And in addition to these, just before the 40 years after the construction, if the utility want to extend the life, they will submit the application for approval of the extension of operation period. And then at most, the Japanese utility can operate the nuclear power plant for 60 years. Could you go next? Thank you, Miguel. So for the soundness evaluation process, we need two maintenance methods. So ensuring the long-term soundness is really important. So for this purpose, so we need two evaluations are necessary. So one is for the current state, and the other is for the future state to the end of the continued operation. So this is an example. This is an example of the case of the carbonation. This is quite familiar, all of you probably. And for the we can do the small destructive evaluation for the concrete structure, and then we can get the carbonation depth. And based on this information, we can evaluate the soundness of the concrete structure at the current state with respect to the carbonation process. If the carbonation depth is less than the cover depth, so meaning that there is no risk of the carbonation-induced corrosion of the rebar. But the utility have to evaluate the state in future. If they want to operate the nuclear power plant for 20 years, based on the information of the current state and the material properties, they have to predict the state at 20 years later. And for example, based on the root T law, we can predict the carbonation depth in the future, 20 years later. And then we can evaluate the soundness of the structure. So therefore, like the procedures, we need two kind of the evaluation procedures. And if it is reasonable, there is a certain amount of discretion in the way you think. So this is just the example of the manner example of the consideration. So you can use any kind of tool, and if it is reasonable from a viewpoint of both engineering and science, it should be accepted. So so there is a kind of freedom to do the research on this kind of topic. So Miguel, I return to you. It muted. Miguel, it's muted.
Thank you. So I'll talk a little bit about the aging management in Finland, and this is defined in the YVL guide A8, aging management in a nuclear facility. And the regulator in Finland, which is STUK, has adopted a different approach where it has specified the aspects that need to be addressed by an aging management program of a power plant. But they allow the power plant to decide how to address them. So describing aging management or describing the procedures and identifying the aging mechanisms, there's no specific guidance for this, but the utilities have to take the initiative and show to the regulator what procedures they have in place, how they plan to identify foreseen and unforeseen aging mechanisms. So the guidance comes from the regulator, but it's the onus is on the utility to demonstrate that what they have adopted and put in place can fulfill the regulator's demands. And I have a list here of some of the aspects that the power plants have to fulfill. For example, they have to document all the procedures, or they have to have procedures in place that identify aging mechanisms, existing or new aging mechanisms. So how do you identify new aging mechanisms? This obviously means that you need to be up to speed with R&D. And I have another slide which shows a little bit more, and I'm not going to go into detail in this, but this document is complemented with an annex at the end, and this annex has a detailed list of aging mechanisms that might occur at nuclear facilities as an assistance to the power plants. And if you are interested in reading this document, it's quite a long document. I leave you the link to the website where this can be downloaded. So all the Finnish regulator guidelines are in English and Finnish and Swedish, and they can be downloaded for free from this website. So I leave you that link if you have more interest in going into that a little bit deeper.
So this is our R&D in support of nuclear power plants, long-time operations, aging issues. So actually, the many institutions organizing the committees, they identified what kind of R&D is needed in the future for the nuclear power plants. So based on the information from USNRC, EMDA, SNTP, ENSREG, IAEA, IGAL, New Guinea, these are the list what kind of research is needed for the NPP LTO, long-time operations. I didn't read everything, but afterwards, please check this kind of list. I think if you find interesting, I think that this kind of the list of the research topic needed from the Nuclear Power Plant Society will be interesting.
Yes, thanks, Ippei. Yes, definitely look at this quite comprehensive list of topics, and I'm sure that there are also many more. So coming towards the end of the presentation, we would just talk a little bit about projects in Europe and projects in Japan that are addressing aging management issues in nuclear power plants. And one project in Europe, which is called ACES, and the title is Towards Improved Assessment of Safety, Performance, for long-term operation of nuclear civil engineering structures. So the goal of this project is to advance the assessment of safety performance of the civil engineering structures, and by trying to address the remaining scientific technology gaps for safe and long-term operations of safety critical concrete infrastructure. I am really happy and lucky to be the coordinator of this project. It started approximately a year ago, and here I have a slide with a general overview of the project. And as you can see, as I said in the goal, we are trying to tackle knowledge gaps, and some of the knowledge gaps which Professor Maruyama has mentioned even are now addressed here. So we have work package 1, which is looking at the aging management aspects in general, looking at the documentation and processes, etc. And then we have 4 work packages which go from work package 2 to work package 5, which are looking at very specific knowledge gaps. Work package 2 is looking at embedded liners and the corrosion of these. Work package 3 is looking at internal swelling reactions. So this is ASR and delayed ettringite formation as well. Work package 4 is looking at delayed strains of the containment building, effects of creep and shrinkage, and temperature and moisture. And work package 5 is looking at the performance of irradiated concrete. So these are the 4 main, let's say, technical work packages. We have a very strong interaction with the end user group. We have 15 or 16 end user groups partners at the moment, and I think we have one partner from Japan, which is Kajima Cooperation, and we're very happy to have them with us as well. And then all this information feeds into a dissemination and communication work package. And I will talk a little bit more about work package 3, which is ASR work package, in the next presentation. So now I will pass over.
Thank you. Japan also have several large concrete projects for the long-term operation of nuclear power plants. I would like to introduce the 2 of them, which we have a role of the technical lead. So first is so-called the Hamaoka project, funded by the Ministry of Economy, Trade and Industry of Japan. And actually, 205 units owned by the Chuba Electric Power are under decommissioning. And the objective is to improve the assessment of soundness of the RC members in the nuclear power plants based on new information from the data harvested from the decommissioning of nuclear power plants, and enhanced non-destructive method validated by the data from the real members and the numerical analysis. So in the project, we took more than 500 cores from the real structure, which have been exposed to the different or specific environment in the nuclear power plants. And we found that there is some similarity with the Roman concrete, and we can find the aluminum tubermarite formation in the concrete under the irradiation condition. So from the viewpoint of scientific, this is also very interesting. And could you go to the next one? Thank you. So the other is a project named the Japan Concrete Aging Management Program on Irradiation Effects. And this is also funded by the METI. And the degradation mechanism of concrete due to neutron irradiation is investigated. The detail will be introduced in my next presentation. Could you go to the next one? And this project is under the umbrella of the US-Japan Civil Nuclear Energy Research and the Development Working Group. So as you see, the many research institutes joined this project. And finally, as the concluding remarks, what I would like to say is the social demands require accountability from all parties involved. And the aging management of concrete structures require the transparency throughout the whole process. And the long-term operation of nuclear power plants needs a solid scientific background. And the engineers should pursue a beyond engineering design process when assessing the reinforced concrete structure performance in the support of LTO. So that is why we should do the research for the LTO. Thank you for your listening.
Thank you very much.
Thank you for a very valuable presentation for the Dr. Miguel Ferreira and Dr. Ippei Maruyama. So there are many valuable information of the nuclear power plant, including the background, current situation, and the management system of nuclear power plants in Finland and the Japan. And also there are remarkable duration phenomena and research project as well. Okay, so I'd like to move on the next session. So among these topics of the overview, so today we are focusing on the internal swelling reaction, which is ASR, and the irradiation of those concrete materials. So first we will have an advanced topics of the ASR research from Dr. Miguel Ferreira. So could you prepare? Yes. So in this presentation, he will give us the general information on the ASR and the big research project which he is currently dealing with. Okay, please start if you can.
Thank you very much. So yeah, now I will go a little bit more specific into the ACES project, and in this specific project also focus only on the ASR aspect. So here we have the table of content. I'll talk a little bit about ASR in nuclear power plants around the world, just to give you an idea of what's the situation. I have one slide summary of what is ASR in case somebody's listening and who doesn't know what ASR is, and what effect it has on the concrete performance. Then I will address the R&D needs of ASR, talk about those, and see how the ACES project is contributing to addressing these R&D needs. So ASR can occur in any concrete structure given the right conditions, and now we have several decades of power plant operation and aging. So now we have already seen signs of ASR in several NPPs, and here is an example of a few of those that are taken from public references. In Belgium we have T102 NPP, and I've already mentioned in the previous presentation the ASR in the ring beam of the containment structure. In Japan, in the Ikata 1 power plant, the ASR has been observed in the foundation of the turbine generator. In the US at Seabrook nuclear power plant, ASR has been detected in many of the concrete infrastructures in that facility. In Canada, in Gentilly 2, also ASR has been detected in the containment structures and at some of the support structures as well. So basically, given the right conditions, ASR will start to manifest itself independent of what type of structure it is. And so what is ASR? Basically, it's a series of chemical reactions that occur within the concrete, and these involve three main parts. The first part is a reactive aggregate. This means some form of reactive silica, amorphous silica, and this is attacked by the second part, which is the hydroxyl ions, OH minus, that are present in the pore solution of the concrete. And these ions will help accelerate the dissolution of the silica, the amorphous or the affected silica in the aggregate. And the sodium and the potassium ions will keep the pH in the pore solution very high, and this helps keep the solubility of the silica at an adequate level. And of course, the last part of this reaction is the need for humidity or water, which will act as a solvent and also as a carrier for the hydroxyl and the alkali ions. And if there's enough humidity in the concrete, typically references are over 80%, then there's the formation of a viscous gel, a silicate, sodium silicate or potassium silicate, depending on the alkali ions. And this gel can can move inside the concrete, and with more humidity, it can expand and exert pressures on the concrete and on the aggregate, inducing cracking within. And calcium from the portlandite in the concrete also has a special role in how it might change the viscosity of the gel and induce the precipitation of this gel as well. So concrete starts expanding, first filling up the voids of the concrete, and then when these voids are full, it starts to cause the concrete to crack, and this cracking, as you can imagine, will deteriorate the mechanical performance of the concrete. And the type of aggregate has a very big role in ASR, and some aggregates can be named as early expansion aggregates, so they react rather fast, like some rhyolitic aggregates, and others are considered late or delayed expansion aggregates. For example, some granites have this kind of performance, and here in Finland we have this type of slow reacting granites. So it might be 40 years before we see signs of ASR in our structures here. And so how does ASR affect? Well, the swelling or expansion of ASR, if the structure is unreinforced and if it's more or less evenly spread out, it's volumetric and isotropic. But this is not always the case. Often the concrete is reinforced, and the reactive aggregates are not necessarily uniformly distributed in the concrete. They might be in batches or in pockets. So this gives an anisotropic aspect to the expansion. And when confined, for example, with reinforcement, the expansion is usually redirected along the direction of least confinement. And mechanical properties of the concrete are affected by ASR, for example, tensile and shear strengths and elastic modulus. These are all affected by the occurrence of ASR in the concrete structures. And there are recommendations in guidance documents for affected structures, to start with the monitoring of the width and the extent of the cracks, to build an understanding of how the aging mechanism is affecting and how it is evolving with time. And usually there are crack widths and crack index values that should trigger actions, and these are also defined in guidance documents. What kind of action should be done, testing, looking at the microscope, and looking to understand what is reacting in the concrete and how it's reacting. For owners of infrastructure that is affected by ASR, they usually have typical questions like, can we estimate past expansion? What is the future expansion? How will the ASR increase in time? How can we address ASR? How will it affect our structures? And this is no different for utilities, for nuclear power plants. They have the same kind of questions and the same need for answers. And there are several different types of performance tests that can be conducted in the laboratory. This can assess the reactivity of the aggregates. This can assess the reactivity of a specific concrete mix design. This can the tests can also measure the potential or the residual expansion of a concrete. So we take a core from a specific structure and we see what is the potential expansion or the residual expansion of that. And this gives an image gives us a partial image of how the structure might react to ASR. And ultimately, the goal is to be able to take the results that we get from laboratory testing and take those results and correlate it to some kind of performance of the structure in situ. But this is not something that's very trivial. In fact, it's actually quite hard. And this is where there is still a great need for research. And this is what we are addressing in this project. And some of the factors that affect this process are listed in the slide. And if we think, for example, on one hand, we have a rather small lab sample. On the other hand, we have a 1 meter thick large wall. What is the volume to surface ratio of these two? What are their thermal conditions? How are they different? What is the spatial confinement by own weight, by reinforcement? What are the moisture conditions? what is the alkali availability or the solubility of portlandite or the calcium availability and the spatial distribution of the reactive aggregates, etc. So if we compare these two distinct situations, a lab sample and an in situ structure, they vary greatly. And these aspects, these differences, these factors are what create different reaction kinetics from the lab to the real structure, and they affect the crack formation and the intensity of the swelling. So this is the challenge for us at the moment, how to take the results from what we get in the lab and extrapolate that to performance in the structure and try to start answering some of the questions of the owners. So this is one of the aspects that needs to be looked into further. And but there are many others, and these have been identified in different roadmaps and different R&D needs, and they are listed here in this slide. For example, more representative specimens in testing, looking at multi-phenomena coupling. So ASR doesn't just occur by itself in the structure, it can be coupled to other aging mechanisms, and that needs to be looked into deeper as well. And as I mentioned, looking at conventional laboratory samples versus real scale samples, and there are others there, so I'll let you read through that. Now I want to go a little bit specific into the actual project. And as I said, we have ACES project, which was funded by the European Union, and the goal was to advance our understanding of safety performance of civil engineering. And this is by addressing the remaining scientific and technology gaps for safe and long-term operation of safety critical concrete infrastructure. And I repeat this figure, which I showed in the previous slide, but now we will focus on the aspect of ASR. In that figure, it's ISR, which means internal swelling reactions, because in this project, we actually look at both ASR, alkali silica reactions, and also delayed ettringite formation. But today I'll only talk a little bit about ASR. And the main goal of work package 3 dealing with these internal swelling reactions is to contribute to the assessment of lifetime extension of the concretes affected by these reactions. So now we have a detailed view of the research that's being carried out in this work package. And this work package is being led by a colleague from IRSN in France, Dr. Jacques Jabour. And if you look at the scheme, at the figure, you see that the work package is made up of 4 tasks, and that they feed into each other and also feed into the final task, which is task 4 at the bottom. Task 1, which is what I will talk a little bit about today, it concentrates on the experimental characterization of ASR. So this means increasing the knowledge on the development of ASR in NPP structural environment. And this is by looking at factors such as the confinement developed in massive structures, the coupling between creep and shrinkage and expansion due to ASR, and the scale effect between lab samples and in situ performance. Task 2 addresses modeling and the prediction of long-term expansion of structures affected by ASR in power plants. And the objective of this task is to develop a series of numerical models that simulate the occurrence and the evolution of the swelling, of the expansion in the concrete. And this includes spatial propagation, the mineralogical alterations that can occur, crack formation and intensity as well. And the intention is that the modeling activities will be conducted on several different scales, starting from microstructural and pore scale, and this will provide process understanding, and this continues into mesoscale and macroscale to make prediction on the scale of the real structure. And from these models, we also propose an engineering model, a tool that would help the owners of the NPPs in the decision-making process as well. So this is one of the outcomes for that task as well. The next task, which is task 3, is looking at recommendations on the use of non-destructive testing in concrete. This task summarizes the state of the art in NDE for ASR and highlights the main physical parameters affected by ASR in concrete. And this is will not be actually conducting very much research, but just conducting a review. And the final task 4 focuses on developing a technical basis for regulatory guidance, and so that they can assess ASR affected in the nuclear power plant structures throughout the service life. And this is using both monitoring results and results from testing of course expansion. So the intention here is to help the owners of the nuclear power plants manage their concrete structures that are affected by ASR. And we want to be able to assist them so that they can account for ASR impacts in the engineering calculations of their structures and prove the safety, and especially for the long-term operation justifications to the regulator. So as I said before, I'll talk a little bit about task one. And if you look at task one, you see that on the left side, there's a structural scale and a laboratory scale. So I'll talk about those two different scales in the slides that follow. So starting with the structural scale, and as I mentioned previously, laboratory studies are conducted on relatively small sized samples, and these do not represent or reproduce real conditions of the concrete structure in its performing environment. So kinetics of the reaction, volume to surface ratio, thermal conditions, etc., that I mentioned before, these all vary. So in this structural scale task, the idea was to better correlate the data provided from residual expansion tests. These are the ones made on course with the actual performance of the structures. So the actual structures of concrete, yes. And to study the scale effect on the swelling kinetics, this is based on looking at the large block samples that have been prepared and cored samples which have been tested in the laboratory and measured to obtain residual strain tests. So how has this been taken forward? Very large scale concrete blocks, non-reinforced, were produced. The dimensions are 2.4 by 1.4 by 1 meters. And these were produced under controlled and optimized conditions. And then they were developed to look at specific expansion internal swelling reactions. One is ASR, the other is delayed Ettringite formation, and also the coupling of both of these. So at the same time having ASR and delayed Ettringite formation, hence the 3 blocks. And experimental protocols to accelerate the ASR or the delayed Ettringite formation were developed, depending on the different mechanisms. And these would allow for us to better observe the expansion reactions in the structural scale. So this that I've described now has actually been all the work of the PhD thesis of the work package leader Jacques Jabour at IRSN. So here is some background into the initial part of the project regarding these large concrete blocks. We see the type of cement that is being used, the sodium oxide equivalent, which is relatively high. We used a non-reactive sand and a reactive coarse aggregate. We wanted to achieve longer and greater expansions at longer times. Then we have in a short, how can I say, a brief overview of what the conservation history of the block for ASR was. So for the first 235 days, it was kept constantly in water and at ambient temperature. And then we started the acceleration phase where we put it into a warm pool that you can see in the figure on the bottom on the right-hand side at 38 degrees. And this pool had 13 water renewal cycles. And during each cycle, we measured cracking in the wall, documented that kind of cracking in the wall. And then after those water renewal cycles, the block was again constantly immersed at 38 degrees without any more renewal. So from this experiment, there was also instrumentation. So we were measuring expansion at different heights inside the block and in all directions. And all the sensors were kept, as you can see in the top figure, on 1/3 of the block. So we would have a large part of the block which would be unaffected by cables or any kind of foreign elements inside the concrete. And the data collected from the block are the block itself, the expansion, the cracking index, and the leached alkalis from the block. And this was taken from measurements of the pool water. We have early age cores for residual expansion tests. These were taken at 235 days of age. Final age cores for residual expansion tests as well. Excuse me. And also at the same time the block was cast, we also had cast specimens for residual expansion tests. So there's a lot of concrete and a lot of different information, and the testing and obtaining of these results is now almost complete. We are just waiting for the final residual expansion tests. And after we have all these expansion test results, then we will have all the data and ready to go forward with that. But I want to give you a little bit more information on the actual process itself and some of the results. So here you have a visual aspect of the ASR block. I hope you can see that clearly. The cracking is maybe not so visible in the block. So these deformations and the crackings, these were tracked in the block for more than 3 years. And obviously the cracking is not uniform. The cracks filled with white precipitation, which we measured to be calcite. And we measured the cracking index in each of these cycles as well. And we also measured the leaching of the alkalis in the pool water that was used to keep the humidity in the block in the right temperature. We observe a large longitudinal crack at mid-height and lots of vertical cracks, especially on the top of the block. And as we come to the bottom of the block, we see that there the cracking is smaller and the crack width is also smaller. And the block itself was cast on top of a metal plate, and this metal plate is having a confinement effect, so it's hindering the swelling in certain XY directions at the lower part of the block. And in that small little new figure that appeared there, so here we have the measurements of the alkalis as a function of the different water cycles. And you can see in the beginning, in the first 2 water cycles, there's a very high content of alkalis, and these are obviously being leached directly from the concrete into the water. But after a while, this stabilizes, and only when concrete starts to crack and open up cracks, then do we see again a gradual increase in the alkali content. So as the concrete begins to crack and as the cracks begin to open, there's access to more pathways for water to access and help leach out the alkalis as well. So we made some calculations, and we estimated that approximately 9.5% of the initial amount of alkalis leached. So this is something that is not negligible. And if we think about the kind of tests that we do in the lab with the cord samples that are conserved at high relative humidity, but not immersed in ASR, and very little leaching occurring there, we can already see here another factor that might be influencing the way the results in the lab don't necessarily simulate results in real structures. And then, of course, this acceleration protocol itself might not be representative of all of NPP concrete structures as well. And here we have some more results, and these are of the expansion of the block and the residual expansion tests, and also the cracking index. So if you look at the block, we see, so if you look at the blue, red, and green curve, we see the expansion in different heights. We had sensors that were at the lower third, we had sensors at the mid height, and we had some sensors, expansion sensors at the upper end of the block. And we can see that as we go from the base to the upper end, the expansion increases in all 3 directions. And this is we already expected this because of the confinement that the base plate is giving to the block. And in orange on the left-hand side, we took the core out at 235 days and did a residual expansion test there, and we see that that's the result. So a little bit about the residual expansion test. These make it possible to assess the damage of ASR and whether this is going to get worse in the future or whether the expansion has stabilized. And it's one of also the main data that is used in numerical simulations and allows to calibrate the chemical processes of the reactions in the models. And it defines a kind of chemical potential of the ASR, defining an upper limit, strain limit for the structure. So even though the swelling in both samples is activated by the temperature, the high temperature, the 38 degrees, we notice that the swelling amplitude and the kinetics differ greatly if we look from the sample on the left to the curves on the right. Firstly, we noticed that in the core, in the lab, there's no latency time. That means that the swelling is initiated as soon as the samples are conserved at 38 degrees, whereas in the concrete block, it took some time before the reaction started. We also observed that the extent of swelling is different. The residual swelling is 0.22 in the core, and in the block, it is in the upper block. If we consider the upper sensors to be the ones that are least affected by this restraint, so most probably those that are most likely to be comparable to the cores, it is 0.17%, and it's been estimated that it might stabilize at 18.5%. So another difference there. And we also noticed that the swelling in the core stabilizes after approximately 400 days, whereas the block, it hadn't stabilized, and even after 900 days of conservation, it was still expanding. So clearly there is a scale effect on the reaction kinetics and on the swelling amplitude. And on the right, we see the macroscopic monitoring of the mockups and the use of the cracking index, and we see that this shows a constant increase even in acceleration phase, and possibly a leveling out phase towards the end there. So what data is still missing? We are still performing the residual expansion tests on the last concrete cores taken from the mockups, and these are being done, of course, at 38 degrees and 100% relative humidity. So the analysis of these results is now the next step, the next phase in the project. And so we have expansion in the blocks, we have expansion in the cast specimens, and the same concrete that's stored in similar conditions. We have expansion in the cores taken from the blocks when the tests were started, and expansion in the cores taken from the blocks when the expansion leveled out. So lots of data collected, and this data provides an opportunity to isolate the effects of scale, because the composition and the environmental variables are relatively constant between the small scale laboratories and the large blocks. And so the next step is try to answer the questions of the owners. Can we estimate the past expansion? Can we estimate future expansion? How will ASR increase as a function of time? How to address ASR? How does it affect the performance of the structures? And this is the way forward for the ACES project. Now moving on to the laboratory scale, and the objective here is to determine which parameters are crucial for the advanced numerical simulations. And additionally, what kind of microstructure and mineralogy output is needed to serve as input for pore scale and mesoscale models. And these two will feed into a task 3. If you recall the general picture I showed, task 3 is where the modeling will be done. So this task laboratory scale is providing a lot of input and data for the modeling in task 3. So to address these two goals, 2 experimental campaigns have been prepared at the laboratory scale. And in the first, the interaction between the expansion to ASR and the mechanisms affecting the delayed behavior of pre-stressed ASR is being studied. And these delayed behavior of pre-stressed reinforced concrete structures, this includes the creep and shrinkage due to biaxial compression constraints. So if you think about a containment structure of a nuclear power plant, many containment structures have vertical and radial or horizontal tendons, pre-stressed tendons, and this is a rather unique type of structure, and very little research has been done how this affects the evolution of any kind of expansive reactions in concrete. Also looking at the effects of shrinkage, endogenous and drying shrinkage, and also early age hydration, heat release, and thermal deformations. And in the figures there, they're not exactly related to the work that I'm talking about, but they're some of the pre-modeling that's been done. So the development or the preparation or the assembly of a finite element model, and we can see in the top part cross-section where we show the location, for example, of vertical tendons, and in the bottom figure we see a 3D imaging highlighting a few of the horizontal or radial tendons. And looking a bit deeper at the creep and shrinkage due to biaxial compression constraints, this is ongoing at the moment, so I don't really have much more information I can provide. But several studies were done, preliminary studies were done to see which would be the optimized dimensions of slabs to be taken into account, and a number of parallel tests taking into account the number of tests that we want to do, taking into account all the variables, and also the space available in the laboratory. So these are some of the constraints that we have, and that if you've conducted any kind of research, you understand very well. So the chosen slab was 40 by 40 by 10 centimeters, and these will be biaxially compressed and maintained at different conservation temperatures. So the specimens are not reinforced, and they are compressed by a steel frame, and you can see that in the image, the finite element modeling that was done. And the stress will be applied by hydraulic jacks, and then these frames at the same time will be placed in a pool of water in the case of ASR, or in different temperature and humidity conditions in the case of creep and shrinkage. So here are some of the variables that we are dealing with. Different types of pre-stressing. So we'll have samples that are not pre-stressed, samples that are uniaxially pre-stressed, samples that are symmetrically biaxially pre-stressed, and samples that are asymmetrically biaxially pre-stressed. And if you look at temperature and humidity conditions for the ASR samples, they'll be placed in water at 38 degrees. But if we're looking at delayed strains, these are kept at 50% relative humidity and are stored at 20, at 38, and at 50 degrees. So at 3 different conditions, and these reflect different temperatures that can be found at nuclear power plants, different working conditions. And 3 different concrete mixtures will be used as well. And one of these will be the Vercor concrete, which is another project that was undertaken by EDF in France, where they built a 1:3 scale of a containment building and have tested that quite comprehensively. So we want to be able to build on the data received from that project and complement it with data from this one. So we'll be using the same concrete mix there as well. The chosen temperatures are to accelerate the ASR. And as I said, they represent different kind of locations in different types of ages of concrete at the different power plants. So the challenge really is to be able to isolate the different mechanisms that are acting on the different aging mechanisms and on the delayed behavior of concrete. And the second part of the laboratory scale tests is just a simple mineralogical and microstructural characterization, of course, taken from the real scale blocks. So if you recall about those large scale blocks that were tested, we will take additional cores from those and do a very comprehensive list of tests to obtain data. And this data is to serve as input to the pore scale and mesoscale modeling. Excuse me. And if there is any further need for laboratory testing with regards to either ASR or delayed Ettringite formation, then these tests will be performed as well. So there is that possibility. And this brings me to my last slide, which I would like to conclude with, and just say that ASR is a really complex deterioration mechanism, and that problem solving of NPPs affected with ASR require really detailed understanding, and these are really normally very complex situations and often require rather deep knowledge and sometimes even further R&D support. And there is really no quick solution to deal with ASR. We need good observations, monitoring, understanding of how it is performing with time. We need to perform adequate petrography. We need to understand type of expansions, and we have accelerated tests for those. We need to reassess the structural performance based on the data we've collected from the change in mechanical properties and the type of expansion that we can expect. And we need to keep up to date with scientific literature. We need to see what is the novelties, what have we learned, and how can that affect what we want to do. And especially for NPPs and aging management, a good practice is also to have a second opinion, request a second opinion or a peer review of all the steps in the processes that you have trying to deal with ASR from an aging management perspective. And of course, very important is to learn from the operational experience of other nuclear power plants and other large infrastructure owners like road authorities or dams. There's a wealth of information out there, and we need to reach out and talk and discuss and learn from the experience of others as well. And with that, I end my presentation, and I thank you very much for your patience, and I hope that we have some interesting discussion later on as well. Thank you.
Okay, thank you so much for your very interesting presentation. Yes, it's very difficult to connect the experimental data to the structural scale. Yes, so yes, so now I'd like to start the short Q&A from audience, but due to the time limitation, so I have to move on the next session. So yes, the next presentation is from Dr. Ippei Maruyama, and his topic is the concrete degradation due to the neutron and gamma ray irradiation. Oh, now maybe the slide is presentation mode.
Oh, really?
Yes.
I'm not
表示設定もあそこですね。
okay.
はい。
Is it okay? Are you okay now?
Now it is not okay.
Okay.
How to say it? It's enlarged.
Okay. So
Now it's okay.
now it's okay.
Yes.
Is it? How about this?
Yes.
Okay. Well, okay. I will start. Thank you very much. Today I will talk about the concrete degradation due to neutron and gamma ray irradiation. But well, I like to, this one. Okay. So the first, I'd like to acknowledge the project, which is relevant to the following research results. The project was conducted from 2008 to 2016 and funded by Japanese Nuclear Regulatory Authority. And in this research project, Mitsubishi Research Institute, Kajima Corporation, and MRI Research Associates contributed to this research. And first of all, for the long-term operation of nuclear power plants, there is a need to evaluate the soundness of the reinforced concrete members, which are exposed to the neutron and the gamma ray irradiation environments. So as you see, in case of BWR, the primary shielding wall and RPV pedestal is the target member. And in case of the P-pressurized water reactor, this is the primary shielding wall is also the target member. And to evaluate the soundness of the RC member and the neutron and gamma irradiation environment, previously for the first neutron, 10 to 20 neutrons per square centimeters, meaning that how many neutron particles attack to the target, the concrete, is used for the reference paper, reference level. And in case for the gamma ray irradiation, 200 megagray is used. And these values are based on a Hilsdorf's review paper, which was published in 1978. And we look at each of the experimental conditions. The use data shown in the Hilsdorf's paper is not from the concrete used in a light water reactor or not appropriate condition for the light water reactor. So therefore, we noticed that there was a gap and the scientific background on this issue was not sufficient at the time. So by the way, do you know what is the radiation in this volume expansion of concrete under the neutron irradiation conditions? Concrete can be expanded because of aggregate. This is a result of the metamagnetization of alpha quartz. Metamagnetization means that the crystal structure is destroyed by the radiation. Look at this picture. This is the transmission electron microscopy result of the alpha quartz. And this pattern is the electron diffraction pattern, reflects the crystal structure of the alpha quartz. After doing the observation, after several minutes, due to the electron irradiation, the electron diffraction pattern is disappeared. And as you see, we see some difference from the previous picture after the electron irradiation. And if we're using the electron energy loss spectroscopy, we can identify the electron density change. And based on this value, we can guess the density change of the alpha quartz under the electron irradiation environment. And we found that the 4% reduction, meaning that about the 4% expansion of alpha quartz was found under the TEM observation. And when the neutron was irradiated to the alpha quartz expand up to 18% in volume. This is more remarkable than the results by electron irradiation. And currently, the atomic size voids, which by the bombardment of irradiated ions or neutrons, are known to contribute to this swelling behavior. Based on a review paper by Bykov, the group, this swelling is affected by the temperature. So if in case of the low temperature, around the 220 degrees C, the expansion is quite sensitive. While the irradiation happens, the quartz is irradiated and around the 100 degrees C, we see such gradual expansion, swelling behavior under the irradiation. This mechanism is not clarified yet. In a lower temperature, we know that the temperature has a large influence on the expansion of the alpha quartz, and also that this expansion of the alpha quartz has a large influence on the property change of the concrete. And based on this kind of literature review, we started the new research project. And in this NRA project, we have set 4 sub-projects, and those are neutron irradiation research, gamma ray irradiation research, and heating and drying impact experimental researches, plus numerical analysis project. When the neutron is irradiated on the concrete, secondary gamma ray will occur, and when the energy of the neutron and the gamma ray is absorbed in a concrete, it becomes heat, and the elevated temperature will bring the drying impact. Therefore, to identify the impact of the neutrons, we know about the impact of gamma ray as well as the impact of the heating and the drying. That is why we set these 4 sub-projects in this project. And today, I would like to introduce the neutron irradiation experiment mainly. For the neutron irradiation experiment, we use the deep 2 reactor owned by IFE Norway, which has been already permanent shut down recently. And this is a heavy water reactor, and this is suitable since the gamma ray flux is reduced during the irradiation. And as I mentioned, during the neutron irradiation, we see the large temperature increase inside of the specimen. So therefore, to get appropriate data, design of specimen is really important. And in our case, 4 centimeter diameter concrete specimens were used based on the estimated temperature distribution inside of the concrete specimen. And so this is the view of the inside of the reactor. And this is the schematic figure of the design of the capsule, which store the specimens during the neutron irradiation. And in the capsule, for the irradiation experiment, we set 4 different neutron irradiation levels, and 2 different concrete specimens are prepared. The water to cement ratio is common and is about is 0.5, and only the type of the coarse aggregate is changed. And one is the outer tuff, who has a large amount of quartz inside, and the other is the general ordinary sandstone, whose alpha quartz content is about 50%. And in addition to these 2 concrete specimens, we also put the small aggregate specimens here. So 6 aggregate specimens were prepared. And at the center of this setup, we put the hardened cement paste specimen as well. And regarding the aggregate, we prepared 6 different aggregates prepared. 1 is limestone, and 5 is the sandstone, which taken from over the Japan. And this is the information about what kind of rock-forming minerals exist in the selected aggregate, a used aggregate. In case of aggregate A, almost all the minerals is alpha quartz, but the other is the amount of quartz is changed like this. So we will see the impact of the alpha quartz amount on some property change of the aggregate after the neutron irradiation in this case. And we also prepare the dummy specimen. So we make the dummy specimen to get the data after the heating experiment. As I mentioned, during the neutron irradiation, we will see the temperature increase in a specimen. Therefore, to separate the impact of the neutron respect to the temperature, we also did the heating experiment. So I would like to introduce experimental results. The first, we identify the cracks on the surface of the concrete. This is evidence that something happens in a concrete after the irradiation. And these are the data of the mass change and the length change of the specimen after the neutron irradiation. X-axis is the neutron fluence, meaning that how many neutron particles attacked the concrete specimens. We see that the large drying impact. The capsule maintained the pressure to keep the safe condition inside, and during the irradiation, vapor, oxygen, and hydrogen are produced due to the elevated temperature and the radiolysis. And the bulb releases these elements from the capsule. Therefore, we will see the drying impact during the irradiation. On the contrary, we will see the expansion. The magnitude is quite large, as you see. In case of the concrete with the coarse aggregate with a high amount of alpha quartz, it's expanded to the 2.5%. And in case of the concrete, who contains the sandstone, about the 50% content of the alpha quartz, showing the less expansion, but still the amount of the expansion is very large. It is almost 2% after the neutron fluence of the 9 by 10 to 19 Newton per square centimeters. So then, when we look at the strength change or Young modulus change, these are the experimental results of the compressive strength and the Young modulus of concrete after irradiation. The data are normalized per the properties of the seal condition at the same age. So as concrete is expanded, the property was deteriorated. In case of the compressed strength, more than 40% reduction was confirmed here. And in case of the Young modulus, 70% reduction was confirmed here. In case of the highest neutron fluence case, we have some trouble. So I will not say in detail, but due to some capsule restraint condition, make some increase of the concrete specimen. So that is why we see some anomalous behavior at the last neutron fluence case. And this is the experimental results of the heating experiment. We copy the heating history of the specimen under the neutron irradiation. And we copied it, and after the history of the same temperature, we will see about the 10% or 50% reduction of the compressive strength. And in case of the Young modulus, we see about the 20 to 25% reduction. So only for the heating or drying impact, still we have some little deterioration. Therefore, when we think about the impact of the neutron irradiation, we can say something like this. So this data plots the experimental results of the compressive strength ratio as a function of the neutron fluence. And we also plot the previous experimental data by the Russian research group or European research group. And based on this, up to the 20% or 20%, we can say that this can be happened due to the heat and drying impact. So above this value, it could be, we can say that this can be happened due to the neutron irradiation. So therefore, it can be concluded that the neutron irradiation impact was confirmed above the 1/10⁻⁹ neutron per square centimeters, which is one order smaller than the used reference value. But this is quite consistent to the conclusion of the Hilsdorf, and also the reference value proposed by the United States, US NRA. So the short summary, the concrete was expanded due to the neutron irradiation, and the compressive strength and the Young modulus are reduced due to the neutron irradiation. So the problem is, or we have to identify the source of the expansion, source of this expansion. So now we move to the aggregate experiment results. So as I mentioned, 6 concrete aggregates were irradiated and measured the range change. So 5 aggregates are sandstone, and the last one is limestone. Our working hypothesis was that the quartz is sensitive to the neutron irradiation. Therefore, sandstone aggregate who contains a different amount alpha quartz are prepared. The contents were quantified XRD lead beta analysis. And this is how the aggregate looks after the neutron irradiation. We see some minor cracks on the surface of the aggregate specimen. And this is the data of the aggregate expansion as a function of the amount of alpha quartz with the different neutron fluences. The blue, orange, the gray, the yellow, these are different neutron fluence levels. And as you see, in the low level of the neutron fluence, the expansion of aggregates is almost linear to the quartz content, as you see. While in the higher neutron fluence cases, a fluctuation was confirmed like this. This indicates that the rock-forming minerals other than the alpha quartz is also possibly affected by the neutron irradiation. That is why we see this kind of fluctuation here. But in case of lower, the impact of our alpha quartz is quite large. This is the result of the X-ray diffraction, the pattern of the aggregate B, the sandstone, with the different neutron fluence levels. Red is the lower neutron fluence level, and the blue is a higher neutron fluence level. We confirm that the quartz peak, the Q, a peak belonging to the Q, and alubite peak here and here. And we can confirm that the peak shift to lower 2 theta angle, which indicates that the structure expanded under the neutron irradiation. And also the peaks become weak after the neutron irradiation, and some disappeared after the irradiation, which proves that the crystal structure is destroyed after the neutron irradiation. And finally, I would like to shortly introduce the result of the hardened cement paste. There is no or almost negligible volume change after the neutron irradiation. And also we see the increase is the Becker's hardness of the hardened cement Becker's hardness as a function of the neutron fluence here. So therefore, we can conclude that the hardened cement paste is durable under the neutron irradiation environment. And strength was increased, but the aggregate was expanded. So regarding the sandstone, quartz is dominating factor. So feldspar group may contribute to the expansion in higher fluence level. So metamictization was confirmed. So neutron destruct the crystal structure of the alpha quartz and feldspar. So the conclusion that the source of the concrete expansion and the resultant degradation due to the metamictization. So based on this knowledge, we also do we continue the research. But I think that the time is limited. I would like really shortly explain this our current the research. Based on this, based on the knowledge of the NRA project, we have to cover all the aggregate used in the nuclear power plants in Japan. So based for that, any kinds of the rock forming minerals in used concrete aggregate, we have to investigate the relationships of the expansion of the rock forming minerals and the neutron fluence. And based on the molecular dynamics and the neutron irradiation experiment, we are collecting the data. And at the same time, aggregate level, we do the irradiation experiment. And above this size, we are doing the numerical analysis. Based on the rigid body spring network model, we can identify, we can make the bridge between aggregate expansion and the degradation of the concrete properties, compressive strength, Young modulus, tensile spring strength, whatever. And above this, we try to evaluate the behavior of the very thick concrete wall, which is irradiated from the one side, and also try to evaluate the seismic performance of the cylindrical structure, which is affected by the neutron irradiation. So all kinds of the scales are investigated currently. Thank you for your attention. This is all my slides. Thank you very much.
Okay, so thank you for very interesting presentation. So yes, I tried to open the short Q&A, but due to time limitation, I have to move on the next session, which is the panel discussion. So we already have some of the question and comments from the audience. So based on these discussion. Sorry, the discussion based on these question and comment will be in the panel discussion. Okay, so could you start, Professor Nakurai?
Yes, so thank you very much. So I'm Kenichiro Nakurai of Hiroshima University. Of course, I really appreciate the great presentation from the presenter today. So they are really excited presentation to understand the current issue of aging management of nuclear power plants. So at the beginning of this discussion session, I'd like to introduce one question from the audience. So because of the time limit, I will introduce one, the first one. So are there any project on the technology related to the decommissioning and recycle or reuse of concrete structure for nuclear power plants? So
we do projects on the technology.
Yes. So first,
I can start.
Yes, please.
Thank you for that question. Obviously, decommissioning is a very big topic now, and in Europe, a lot of effort and a lot of research is going into decommissioning. So when we think about the areas that are receiving funding for research, of course, nuclear safety is one main area. Waste repository is another area, and decommissioning is also another area. So the answer is yes, there are many decommissioning projects ongoing, even at a national and international level, funded by European Union or other funding. Specific examples I cannot give, I'm not involved in any. I know that at VTT we have our own mini decommissioning project. We have a research reactor which we have shut down in 2015 or 17. And we have now begun the decommissioning of that reactor itself, but that's a rather small project. And so the answer is yes, there is lots of research and lots of projects ongoing, but unfortunately I can't give you an example of specific, as I'm not directly involved in any of those. Regarding the second part of the question, if I understood correctly, it was about the reuse of concrete from the decommissioning. Is that correct?
Yes, I think so, yes.
Well, if the concrete is not contaminated, so if it's contaminated, it has to go to repository for waste. If it's not contaminated, I don't see why not. It could be used as a raw material in a sense, or even in structural elements. The question rather is whether there is some kind of legal limitation to that. But very interesting question. Thank you.
Okay, thank you very much. Yeah. Professor Maruyama, do you have any additional information?
The situation in Japan is quite similar. We have the project or research on the technology related to decommissioning. Of course, we have to decommission. We have to do the decommissioning. Regarding the recycle or reuse, there was, the recycled concrete technology is originally in Japan is aiming to replace the nuclear power plants in the same sites. So without bring the aggregate outside of the site, which possibly be contaminated, is not good for the social environment or social understanding. Therefore, the utility were to reuse these kind of aggregate. But I'm not sure that this kind of thing is still under. Yeah, of course, many researchers are interested in recycle or reuse of the concrete and the concrete aggregates, but I'm not sure it is strongly relevant to this decommissioning nuclear power plants. That's my answer.
Thank you very much. So now we'd like to move on to the a little bit specific discussion for each presentation. So Dr. Ferreira, so could you share your slide number 10 with us again? So here could you share your slide number 10? So it shows the research framework of the big project, WP3. So the second presentation in your own presentation, and slide number
10?
Yes, number 10.
Is this one?
Yes, yes. So first, I'm interested in the research flow in this figure. So I understood. So you started to the structural scale test to understand or to predict the behavior, not from the small laboratory scale, but to the structural scale, then the laboratory scale, then the prediction model. So it is your typical the flow chart to the study the concrete behavior or ASR behavior for the nuclear power plant. So I mean, so
well, I think I understand the question. Thank you very much, Professor Nakarai, for the question. I understand what you mean, because we're starting at a structural scale, and it looks like it's feeding into a laboratory scale. Yes. And we would expect usually to start in the opposite direction. I think maybe the issue here is the naming of these scales might have not been the best kind of names. So basically here, what we are looking at in this slide is the relationship between the lab sample performance and the structural scale performance. But the connection from here to here, this is because we take cores from the blocks and we characterize the mineralogical properties of the concrete. So that's why it feeds into there, because that kind of basic information, the mineralogical composition of the concrete and all these other kind of tests, they come from the blocks. So it gives the impression that the structural scale is feeding into the laboratory scale, but that's not necessarily correct. It's just that in that specific case, the source of the information is the blocks. And so the information comes from the blocks and into this direction. But and I understand that can be misleading.
No problem. Then from this figure, so all results are going to the recommendation and the guidance for the assessment. So for example, so can you directly utilize the laboratory test, especially the expansion test for the guidance for assessment?
So if you're asking if the expansion tests can be used
now for this the practical decision.
So if I understood correctly, the question is, can expansion tests be used by the owners of nuclear power plants to assess the performance of this?
Yes, yes.
Of course, it's one of the possibilities that they have. So if the owner of a power plant has a concrete structure that's affected, and it wants to assess what is the condition of the structure and how it's going to perform in the future, and what kind of structural performance changes have occurred. One of the tools, one of the inputs is the expansion test. So yes, it can be used, and it should be used. So, but the answer is yes, it should be used, and it should feed into all the assessment that they do. In providing assurance to the regulator that the structure is okay. So that is one part of the puzzle that provides the whole picture of how the structure is performing. I'm not sure if I answered correctly the question.
Yes, basically. But so as you mentioned, so the ASR is quite complicated behavior, especially for the structural performance. Yes. Because of the three-dimensional confinement. So my question was, can you apply the material that testing data for the assessment of the real concrete structure? So that directly.
So you're asking me if if it can be used directly?
Yes.
But well, I think that's what we are looking into in this project. So that's exactly the goal in the project, is to be able to conduct these kind of tests and then have the tools that allow us to use those and extrapolate them to structural performance. I think currently now there's a certain amount of unknown. We can't use those results directly. They give us an indication of what might be the maximum expansion we can expect in the structure. And that gives us an indication of the type of damage that might be induced in the structural performance. But currently, we can't say that this gives us a direct relationship to the performance of the structure. We don't have that understanding yet. But that, I think, is exactly what the project is trying to address. That's exactly what we are trying to look into and establish how we can go from a laboratory sample and assessment of expansion, and how we can, what steps do we need to take, and how can we go to a structural level and say we can expect this kind of performance at a structural level.
Thank you very much. So, Professor Maruyama, so do you have any additional comments on this discussion?
No, not really.
No.
Yeah, I think the people who are dealing with ASR or these kind of things think the similar way.
Okay, thank you very much. So next, I have another specific question to the Professor Maruyama's presentation. So today, you clearly explained the detailed mechanism of the aggregate expansion by the neutron radiation. And also you explained the main factor of aggregate expansion. But I think the main target is existing the power plant. So I mean that you cannot select the type of aggregate. And I think it's very difficult to control the radiation. After understanding the detailed mechanism, so how will you utilize your result for the assessment project?
First, with regard to the NRA project, we posed several procedures to evaluate the soundness of the concrete structure which is affected by the neutron and the radiation. So if, for example, if the calculated neutron fluence is less than the 10 to 19th neutron per square centimeters, all the utility can say that the specimen is safe, or this member is safe. And even if beyond the 10 to 90s, we also show some procedures. For example, evaluate the compressive strength deterioration based on expansion of the aggregate. And they can estimate the reduction of the compressive strength and can compare with the design strength. And if this kind of strength is beyond the design strength, they can also say that this is still sound. And we also propose that the soundness evaluation method for the structures, which is partially affected by the aggregate expansion. So, I didn't. Today, I explain the phenomena more detail rather than how we can use this kind of the knowledge produced in our project. But the final goal was to propose these kind of procedures to evaluate the soundness of the structures. So based on this, the procedures, they can use our the developed the knowledge or the found knowledge.
Okay, thank you very much. So due to time limitations, so I will have to give the final question maybe. So today, so we had an excellent overview of the aging management of concrete structure for power plants. Then I want to know what is the strength or advantage of the Japanese study in this field, if you have any idea. So Dr. Ferreira, so do you have any comments on the current situation of Japanese study or Japanese technology?
Well, I think in the initial presentation where we gave an overview of the aging management, a brief introduction to aging management, if you will, we mentioned in the conclusions that we need to pursue the latest understanding of knowledge, because only through that pursuit can we understand exactly what is happening and take the right measures to counteract or to address that. And I think that the research that's coming out of Japan, and I'm more familiar with the work that Professor Maruyama is doing, but with regards to irradiation of concrete and aggregates, I think they are world leading in that sense. So they have identified the need early on, the gap in knowledge, and quickly understood before anyone else that if we want to extend the lifetime of the plants from 40 to 60 years, this is an issue we need to answer. This is a question nobody knows how to answer, and we need to answer that question. So very early on, this research started in Japan, and after that, very quickly, it has expanded across the world. And so I think in that sense, in this specific regards, they have identified the need and pursued the need for that knowledge and the excellence in that area, and I think that has been achieved successfully. So in that sense, I really appreciate the contribution that has been made for the well-being of everyone, of course, in that area.
Thank you very much. So, Professor Maruyama, so do you have any additional comments?
Oh, yeah. And also, I think a little bit different perspective, but I think the international collaboration is also very important. I mean that, for example, the irradiation experiment is very expensive, and it is very difficult to conduct the many kinds of the parameters. So therefore, getting some consensus or getting the information exchange is really important with regard to these kind of things. And also, yeah, in case of Japan, we have to think about the seismic performance. This is a little bit the special rather than the European countries or other OECD countries. But still, we can contribute the something based on a seismic performance evaluation process to the concrete science, which is necessary for the LTO of the nuclear power plants. So what I want to say is they're exchanging knowledge internationally and try to find the position or the difference between those, and identify those things is very important for the starting process. Yeah, that's a short remark.
Thank you very much. Very important and strong message for us. Thank you very much. So it's almost time to close this discussion session. So I'd like to pass to the Miura Sensei again.
Yes, so thank you very much for the fruitful discussion for Dr. Miguel Ferreira, Dr. Ippei Maruyama, and Dr. Keiichi Nakarai. So through the lectures and the panel discussion, we could understand the current situation of the internal strain reaction of the which is SR and the irradiation of the concrete in nuclear power plants. So yes, I think there is some of the difficulty of the management of nuclear power plants. Somehow we have to manage using a limited knowledge and limited technology. And I think in the future, we have to overcome this problem to improve the that limitation of the knowledge and the technology. So this is my yes, what I obtained from this webinar. So I hope the audience also obtain something from this webinar. So thank you so much. on behalf of the organizer of the FCT webinar, I deeply appreciated it for your great cooperation for the invited researcher and invited moderator. Thank you so much. And at the end of this webinar, we would like to announce the next FCT webinar. So I would like to share the information. Can you see this? Can you see this?
Not yet.
Okay.
It's giving the front slide.
Just a moment. How about this?
Yes.
Okay. Okay, so please explain about it, Professor Nagai.
Okay, thank you very much, Dr. Miura. Hello, everyone. I'm Nagai, the University of Tokyo. And then, let me introduce the next seminar. The next seminar is on the simulation of concrete and reinforced concrete structures using discrete analysis models. So in this seminar, we'd like to invite, yes, again, two leading researchers. One is from US, Professor John Boranda at the University of California, Davis. And the other is from Japan, Professor Hikaru Nakamura at the Nagoya University. So they are the leading researchers on the simulation using the discrete analysis model as shown in this slide. Then Professor John Boranda, maybe he is the first researcher who applied the rigid body spring model RBSM to the concrete fracture programs. He has maybe over 30 years experience and leading this field. And then on the other hand, Professor Nakamura, he's, especially in these years, he's actively doing the many researches using the this method, including the shrinkage and collusion as well, and finally try to evaluate the structural performance and so on. So I hope you join the next seminar as well. And then the tentative schedule of the seminar is maybe January or February next year, or at the end of this year. But anyway, we'll announce you once the schedule is fixed. Okay, thank you very much.
Okay, thank you. So the announcement. So yes, next webinar is slightly, completely different direction of the research from the second FCT webinar. But the key point is, I think, the crack information. So internal swelling reaction is also important point is that the crack, and the discrete model is the target is reproducible of the crack itself. So that is related to each other, I think. So I hope that all of you will attend also the next webinar. So thank you so much for your attendance today. And that is all of the event of this webinar. Thank you so much.
Thank you very much.
Thank you very much.
Thank you very much.